This presentation is part of the TI-Nfocus AP Calculus video series. In this video, I'll discuss a specific concept associated with the 2018 AP Calculus exam, free response question AB3 BC3, namely concavity and points of inflection. My name is Steve Kokoska. I'm a professor at Bloomsburg University of Pennsylvania, and I'm a former AP Calculus chief reader. Here's an outline of the information presented in this video. I'll begin by motivating or discovering a definition of concavity. And this will lead us to the concavity test, that is, how can we find the intervals on which the graph of a function is concave up or concave down? Then I'll focus on points of inflection, a definition, and how do we find them? I'll try an example. I'll talk about the second derivative test. And finally, I'll leave an AP Calculus type example for you to consider. Let's start by trying to determine what f double prime tells us about f. Here are the graphs of two increasing functions on the interval a to b. And for now, just focus on the graphs of these functions, not the tangent lines. Even though f and g are both increasing on the same interval, their graphs look different. They bend in different directions. One bends downward and the other upward. Calculus can help us distinguish between these different characteristics. Now consider the graphs of f and g with the tangent lines drawn at a few points. Notice that the graph of f lies above its tangent lines, and the graph of g lies below its tangent lines. This is the property that leads to the definition of concavity. Here is a definition of concavity. Let's let f be a differentiable function. F is concave up at a if the graph of f is above the tangent line to f at a for all x in a neighborhood containing a, but not equal to a. And similarly, f is concave down at a if the graph of f is below the tangent line to f at a for all x in a neighborhood containing a, but not equal to a. Here's a closer look at this definition. Remember, the concept of a neighborhood containing a means simply an open interval containing a, not necessarily symmetric. And very important here, the concept of concavity is defined in terms of a single number, not an interval. That means that the graph of a function can be concave up, concave down, or have no concavity at a number. Here are some graphs to illustrate this definition. In this case, the graph of f lies above the tangent line in a neighborhood of a. Therefore, the graph is concave up at a. Here, the graph of f lies below the tangent line in a neighborhood of a. The graph is concave down at a. And in this example, there is no neighborhood of a such that the graph of f is always below or always above the tangent line. Therefore, the graph of f has no concavity at a. Now that we have a definition of concavity at a number, we need some help to determine the intervals on which a graph is concave up or concave down. And the second derivative can be used to help determine these intervals of concavity. In this first figure, the graph of f is concave up. As x moves from left to right, the slope of the tangent line is increasing. This means that the derivative f prime is an increasing function. And this means that its derivative, f double prime, is positive. Similarly, in this figure, the graph of f is concave down. As x moves from left to right, the slope of the tangent line is decreasing. This means that the derivative f prime is a decreasing function. And this means its derivative, f double prime, is negative. This reasoning leads to a theorem, the concavity test. The concavity test says, if f double prime of x is greater than 0 for all x in an interval I, then the graph is concave up on I. If f double prime of x is less than 0 for all x in an interval I, then the graph of f is concave down on I. I think we need to take a closer look at this theorem. The concavity test allows us to draw a conclusion about the behavior of the graph of f if f double prime of x is greater than 0 or f double prime of x is less than 0. Note that this does not say anything about the numbers a, where f double prime of a is equal to 0 or f double prime of a does not exist. We need to determine concavity at each of those numbers separately. We already know that the graph of a function is either concave up, concave down, or has no concavity at a number a. Therefore, given this theorem and interpretation, we should not include a number in two intervals, one where the graph is concave up and one where the graph is concave down. And the point on the graph of f where the graph changes concavity is called an inflection point. And let's get a more precise definition. A point P on the graph of f is called an inflection point if f is continuous there and the graph changes from concave up to concave down or from concave down to concave up at P. Let's take a closer look at this definition. If f double prime of a exists and f double prime of a is not equal to 0, then we know the concavity of the graph of f at a. The graph cannot change concavity at a f of a. Therefore, f double prime of x can change sign only when f double prime of x equals 0 or f double prime of x does not exist. Using the concavity test, we can determine that there is a point of inflection at any value in the domain of f where the second derivative changes sign. So we can use a sign chart if we want to help determine concavity and points of inflection. Remember, a sign chart is not sufficient justification on the AP Calculus exam, but we can still use one to help determine intervals of concavity and inflection points and to lead us to a sufficient justification. So here's a procedure for determining inflection points. First, find the inflection point candidates. These are the values of x in the domain of f, such that f double prime of x is equal to 0, or f double prime of x does not exist. Then we need to screen these IP candidates. Check for a change in sign of f double prime at each candidate. If a change in sign occurs, then x f of x is a point of inflection. If there's no change in sign, well, then the point is not an IP. Let's put all of these definitions and theorems together in an example. Let's let f of x be equal to minus x to the fourth plus 3x squared plus 2. Let's see if we can find the intervals on which f is concave up or concave down and find all of the inflection points. Here is a way to solve this problem. First, find f double prime and factor completely. Consider the IP candidates. Find all those values where f double prime of x is equal to 0, and find all of those values where the second derivative does not exist, and here there are none. Here is a sign chart for f double prime. I drew a number line with tick marks at the IP candidates, and the value of f double prime at these candidates is 0. Then I used either a specific easy value in each interval or argued in general using the factored form of f double prime to determine the sign of f double prime in each interval. And this allowed me to draw some conclusions about the graph of f. Here is an interpretation of this sign chart. f double prime of x is greater than 0 on this interval, and f double prime of x is less than 0 on these two intervals. Therefore, f is concave up on this interval, and f is concave down on these two intervals. The sign chart tells us even more. F double prime of x changes sign from negative to positive at x equal minus 1 divided by the square root of 2. Therefore, f has an inflection point at that value of x, and here's the inflection point. In addition, f double prime of x changes sign from positive to negative at x equal 1 divided by the square root of 2. So f has another inflection point at that value of x, and here's the inflection point. Here's how I use technology to confirm my solution to this problem and to visualize the result. On the TI-Nspire, I first defined the function f, and then I used the zeros command to find the values where f double prime of x is equal to 0. I used this command so the results would be stored in a list. I can then refer to specific values in this list. And here, I evaluated the function at each of these values. This allows me to write the inflection points analytically. Here's a graph of the function f, and we can see the concavity of f in this graph. I used the TI-Nspire Analyze Graph feature to locate the inflection points on the graph. Notice that the analysis on this graphs page is numerical. On the calculator page, we found the exact symbolic values. The second derivative can also be used to classify local extrema for those critical values where the tangent line has slope 0. Here's the second derivative test. Suppose f double prime is continuous in a neighborhood of C. If f prime of C is equal to 0 and f double prime of C is greater than 0, then f has a local minimum at C. If f prime of C double prime of C is less than 0, then f has a local maximum at C. And yes, we need to take a closer look at this theorem also. Now, I'm not going to draw a graph here, but let's suppose that f double prime of x is greater than 0 near C. This means f is concave up near C. Therefore, the graph of f lies above the horizontal tangent line at C. And f has a local minimum at C. We can make a similar argument for a local maximum at C. If f prime of C and f double prime of C is equal to 0, then the second derivative test provides us with no information. We need to resort to the first derivative test to determine whether f of C is a local maximum, local minimum, or neither. And finally, the second derivative test cannot be used if f double prime of x does not exist. And here is one final example for you to consider. Let's let f of x be equal to e to the minus x squared divided by 2. First, find the asymptote on the graph of f. Then find the intervals of concavity and the inflection points. Find the local maximum and minimum values of f. You may recognize the function f from probability and statistics. So let's generalize just a little bit. Consider the function g of x equal to e to the minus x squared divided by 2 sigma squared, where sigma is a positive constant. First, answer parts a, b, and c for the function g. And then graph the function g for several values of sigma, and explain how the value of sigma affects the shape of the graph of g. I hope this video provides some insight into concavity and inflection points, a few AP Calculus type problems, and the use of technology to solve and visualize these types of problems. And just a reminder, there are lots of valuable resources on the TI website. There is material there involving technology and calculus, classroom activities, and lots of calculator tips and tricks for test success.